I've started this video at least 2 times before, and I just could never complete it. I've wanted to make a video where it's like, what is the last microcontroller that you can find in any decent quantity, and what can you do with it? Because it's gotten pretty bad. Well, it's been pretty bad for like, what, a year and a half now? Yeah, but I don't know. It's just like, it's almost like I just need to like just do this. Because what happens is it keeps changing. I was looking at my folders and I already attempted this back in March of this year, 2022. It was going to be with the SAM D11C microcontroller. Let's bring that up. It's unobtainium now. Like, yeah, this one they actually used to have a pretty good stock of. It's a Cortex M0. It's actually not bad. The limitation is there's only 14 pins and, well, what is that? -3 +2 to program. So you're looking at what, 9? So let's see, in stock, exclude marketplace. That's one way they make it look like they have more stock than they do. Most of it's Rochester Electronics, which is kind of a reseller. There's a Cypress Semiconductor microcontroller, 8-bit. Ooh. Okay, now this is pretty cool. Right now, the Raspberry Pi Pico, the RP2040, it's very well stocked. I actually bought a bunch of Pico W's from DigiKey for my next workshop. I am not familiar with Cypress, so I found this guy. So this is like the most plentiful chip that I'm used to programming. A lowly ATmega 8, not a 32.8, an 8. Oh, and even worse, it's an 8L. But hey, they have 84,000 of them. See, now I thought about this with the SAM D11C. I was like, what? How would you use this? Because it's got DMA and all this stuff, but it doesn't have very much RAM, and also doesn't have very much I/O. But it does have USB. So I'm sure some engineer somewhere was like, Eureka! I can use this chip in our product. And then, of course, they bought them all. So let's look at this little guy. Program memory size, 8 kilobytes versus 32 for the stock Arduino. RAM, 1K versus 2, I want to say. So this is a pretty lame chip. And also look at the price. It's really expensive for how lame it is. But there's 84,000 of them. So what I wanted to do in this video was take a look at this, maybe make a little breakout board for it, and see what we can do with this fairly weak but obtainium chip. Here is the chip in schematic view of Eagle. And yes, I still use Eagle. I have the Fusion 360 subscription, which includes Eagle, so I might as well use it since I know it. All right, so here's the chip. Doesn't have a whole lot of I/O on it. I did read the datasheet, RTFM. It has an internal oscillator, so we could probably free up these 2 pins here instead of attaching the crystal as they are like on an Arduino. Over here we have the ISP programmer. I got this from the Adafruit library. That's the standard AVR Mark II programmer. Yeah, so let's just do some housekeeping here. And I am a candle maker, and you don't see me complaining. BFG, I'm a screenwriter. Boy, I'd really like to burn your candles. You burn it, you buy it. Great! I'll be your first customer. You're hardly my first. That's what she said! That is a $250 plasma TV you just murdered. Good luck paying me back on your $0 a year salary plus benefits, babe. So these pins, as I was talking about this with the SAM D11C as well. You can use these pins for other things, of course, but depending on what you hook up, the programmer the programmer wouldn't mess up the things you hook up to the pins. What you hook up to the pins might prevent the programmer from operating correctly when it tries to program the chip. Or, worst case, you just unplug the programmer after each use. Although that's not very convenient. Oh, we got 8 ADCs. That's pretty cool. And then looks like we have a full byte right here. So on one of these, obviously, there's serial, RS-232 serial, external interrupts, a clock. I think T0 and T1 is a timer. Analog comparator input 0 and 1. Although there's not very many peripherals on this chip. I think it does have I2C. Oh yeah, right there. SDA SCL. If only you could use these things to build a car. Cars mostly have, well, the company's been bought out a couple times now, but Freescale. Freescale is the big thing. That's the thing. Like, it's not that they can't build cars, it's they don't have enough chips. So if you were building like a 1975 Jeep, you'd have no problem because there's only one computer and all it does is count to 6. The distributor cap. Well, you know, cars have a CAN bus, a controller area network. It's kind of like, think of it like USB. It's a differential signal, but then it can have multiple nodes on it, so it's kind of like I2C. But it's high speed. It has error correction, obviously, which is important for vehicles. But everything that's connected to that bus, which cars have been using since 1998, I want to say, everything that's connected to that bus needs some sort of node or endpoint. So you might have like a CAN conversion chip, and that would go to a microcontroller, or most modern microcontrollers can do CAN as well. Oh look, it's my gas tank. You know how the gas tank used to be? They'd have a potentiometer in the gas tank. It would be rotated by the float, and the potentiometer would heat up a needle in your dashboard, causing the spring metal to expand and contract, and that would move the needle back and forth. That's how the gas tank used to work. Not anymore. Now it's microchip. Yeah, I've mentioned this before. Like, as someone who likes to build things with microchips, it's kind of depressing how you can't find them anymore. It's like I love watching birds, right? Oh, all the birds went extinct. There's only 3 kinds of birds left. You probably wouldn't like watching birds after that. Even if there's like 3 kinds of birds left, you're like, oh man, I don't really feel like it.
It's the Final Microcontroller. In editing, I'm going to be like, oh my god, how many times did I say that? AT Mega 8L-8AU-ND. 8 kilobytes flash, but AVRs have 16-bit instructions, so it's actually 4 kilowords of flash if you want to get really fancy about it. Because back in the day, sometimes you'd have like 15-bit words, like 16-bit words with 2 bits of parity. Parity, not parody. A parody. Why did the river send a thank you card after receiving a gift? Because it appreciated the sediment. Yeah, I can do this all day. When it comes to dad jokes, he is the one. Whoa. What are you trying to tell me? That I can procedurally make up dad jokes? No. What I'm telling you is, when you're ready, you won't have to. You know what movie I rewatched a couple years ago and held up better than I would have thought was Waterworld. It's not a bad movie, not the greatest movie, but it's all right. It's got a nice, mean anti-hero. It's kind of like the fish with no name. It's also fun to watch that movie and try to pick out the Joss Whedon dialogue. Because he did like rewrites on that. So there's lines that are obviously written by him. One of which I can't repeat on YouTube. But there was one that was in the trailer and it wasn't in the movie. Dennis Hopper, the bad guy, he's saying to a minion, he's like, let's have an intelligent conversation. I'll talk, you listen. It's like, okay, that was definitely written by Joss Whedon. Surface mount boards. I might as well just do all 3 of them. So I use some solder flux, just kind of hold it in place. Now I'll add a little solder. I know you young people might not realize this, but in the past, on the Louis Rossmann real estate channel, sometimes they would have soldering. I know it's like, why would they have soldering on a real estate channel, right? It doesn't make any sense, but I don't know. I guess it was like his hobby or something. So every so often, between taking video of like closed storefronts, he would be like, hey everybody, his how to solder a Mac. I hope he can find enough Macs in Austin, Texas. Thing is, he's never going to have, I mean, it'll never be the same as New York. Because New York was a unique mix of 100% Mac usage and also foot traffic. So even if you're like in Hollywood, everyone's going to use a Mac, but nobody walks in Hollywood. I don't think most movies are even made in Hollywood. Or, well, what is it? It's Hollywood and North Hollywood? I used to love going to New York City. New York City is my favorite major American city. What's my least favorite major American city? Well, I'm from Wisconsin, so take a guess. You are being really whiny for this time of day. What's wrong? Did daylight savings time mess up your cat clock? Seriously, what is it? I gave you greenies, just like the real estate channel. And I picked you up, and what else could you want? You know what you really need? You really need a bath. Everything, everywhere, all at once. Ki Hu Kwan is in it, who of course was Short Round in Temple of Doom. He's really good. It's like, I don't know, I guess he was like a stunt coordinator. That was his job after he was no longer a child actor. But yeah, he's really good in it. He's like, plays Michelle Yeoh's husband. It does kind of feel like I've had some extra time yesterday and today, thanks to the change, which I thought was going to go away, but I guess we're keeping it for another year or something. No, I should have bought headers for this. What are these, 8? I might have some 8 buys. The thing is, I bought this chip like a month or two ago, and then I just designed the board like a week and a half ago. Yeah, that reminds me. You know what movie they should remake? Rocketeer. Oh, I know what you're saying. Oh, Rocketeer was... That movie was my childhood. Yeah, it was good, but it wasn't that good. It's like one of those movies like I loved when I was a teenager and then I revisited as an adult. And it's kind of boring. There's really nothing for the Rocketeer to do. It's like the movie should have taken place in like occupied France. Like, have no stories left. The last story. Oh, that could be a reboot of the Never-Ending Story. It could be The Last Story. Our kingdom used to run off stories. Stories gave us hope. And of course, it would also be a metaphor for, stories. But now, there's no more stories. Oh, and that could be a metaphor for how everything's a reboot or a remake. But then, the truth in the end that they learn is that all stories are kind of the same anyway. But you need fresh stories. It's like, okay, we got a couple thousand years of Moses. Then we just tell the same story again, but it's Superman. What? Oh no, my son, you can't live here. You've got to go someplace that's safe because our planet is exploding or they're killing all the Hebrew children. Oh, I will put you into a vessel and send you off so that you will be safe from danger. Oh, look, you've been found by a kindly person who becomes your surrogate parent, but then later on you realize that you are of 2 different worlds, and now you must make a choice. Maybe instead of The Last Story, it could be like The Last Storyteller. Well, no, I was talking about Math Lords. That was Max and I's idea of it. I used images from, what was it, The Page Master? That animated movie with Macaulay Culkin? Yeah, so there's this kid, and he's like, oh, man, everyone's picking on me and stuff. Oh, wait, it's just Never-Ending Story. But then like he's in the library, and then there's this old librarian with like a shotgun, kind of like in Back to the Future 2. And he was like, what are you doing in here? I just wanted to read a book, sir. Nobody's been in this library in 20 years. And then the guy like puts down his shotgun. I thought kids all forgot about stories. Now they only care about TikToks. And then the hero is like, I care about stories. And then there's like some sort of magical talisman that, I don't know, transports the kid into like some sort of world of storytelling. Oh, now you know where we are. Okay, here you go, Wisconsinites. Yep, I'm going to bring it up. Now you're getting into Story Lords territory. You remember that show back in the 80s? No, like at the end of every episode, they'd have to solve some sort of story puzzle. And then they'd be like, oh, not a moment too soon. And then like the soundtrack kicked in. I can't remember what Thorzul's soundtrack sounded like. But anyway, he had like this motorcycle with a sidecar. And he's got like this henchman. And his henchman will always announce him and say, His Royal Badness, Thorzul. And then Thorzul was like this middle-aged dude with like a goatee and like this black cape and stuff. He would always come up to the kids and I think he was always going to turn you into a statue. He's like, I will turn you into a statue unless you figured out my story riddle. And then, of course, the premise of the episode is the kid who comes from the real world and goes, or our world, and then goes into this fantasy land. He will help out whatever random person in the fantasy world that needs help with the stories. And then, of course, Thorzul always gets thwarted. And then he's like, curses! Get me out of here! And then his sidekick's nickname, or his sidekick's name was Milk Breath. I don't know why, but that's what his sidekick's name was.
Milk Breath, get me out of here!
Then in the final episode, because all right, so these fantasy segments were always bookended by the real world, like the kids that go into school and stuff. But in the very last episode, they find out their teacher is a story lord, of course, and then like, she turns into a special effect, and then she says something about like, oh, the power was within you all along. I'm gonna put these headers in place just to hold it. Yeah, both of my siblings are younger than me, and my little brother is like way younger than me. He's like 11 years younger than me. I would be exposed to like stuff that I probably wouldn't have normally watched if I didn't have like a much younger little brother. See, that's why I thought it'd be cool to make like that Math Lords idea, because I think like there'd be like this like I bet you there's more nostalgia for like 90s edutainment, low budget 90s edutainment than you'd probably think. Although Wishbone, if I recall correctly, was pretty well produced. But yeah, you had that, and you had like MathNet, and of course, Where in the World is Carmen Sandiego? And of course, Where in the World is Carmen Sandiego was a edutainment video game before it was an edutainment show. So I guess that means you need a Mavis Beacon Teaches Typing show. How would you make that exciting? Well, I guess they made Typing of the Dead. Mavis Beacon's Typing of the Dead. I'm going to test this one before I solder the others, just so I don't waste my time in case it doesn't work.
Microchip Studio. This is what you use to program AVR devices and, I guess, microchip devices. I like it better than what was that MP Lab. Well, over here, this is the Arduino driver for LCD. There's not actually a whole lot to it. So what I want to do is I want to port this over. This is a C++ thing because it has objects. So I guess we'll do C++ as well. Atmel8. It's like, I'm an Atmel8. I'm lame. But I'm also the final microcontroller. It never gets old. Yeah, I got old like 20 minutes ago. So that's the thing, I have no idea how many times I've even made that joke until I edit. And then I'll be editing and I'll think, oh my god, how many times did I make that joke? Okay, off camera, I'm going to plug in the power source for the thing. Probably should have put an indicator LED in it. It's kind of barren. Well, no, because I can just plug in the programmer and that'll, if the light turns green, that means green is good to go. Well, I suppose the first thing we need to do is blink an LED. I grabbed those LEDs off of the fish project. I hooked it up to PD7 and PD6. And of course, ground. Check the schematic. PD7 and 6, that's the analog. I think that's a comparator input, so that shouldn't affect anything. We should be able to use, well, not all of this, because like we have to take into account, like this thing is programmed using Mosey Miso clock. So whatever we put on these 3 pins has to also play nice with the programmer. Yeah, we have 2 complete ports. So everything on a microcontroller is a port. Like port D. See that? And see how it's got 8 bits. Port B, then there's blah, 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 8 bits. Port C, see how it's not complete? It stops at PC5, and then these 2 pins are just the ADC. Apparently we can't use them for anything else. And here in the data sheet,
blah, 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 blah. I/O ports. I think it's just going to use the port nomenclature. Blah, blah, blah. Let's just get to the registers. That's all I care about. Okay, so we have the data register, the data direction register, and the input pin register. So data register is where the data goes. Like, we're going to put, we're going to make it a 0, 1 as an output. Data direction is if it's an input or output, and input pins is where you sense the value of the pin if it's an input. So it was PD 7 and 6, so we're going to need port D. Here, let's just grab it from the data sheet. Got that. And then DDR D. Okay, so let's make a binary representation. High, output, output. 1, 2, 3, 4, 5, 6. All right. Port D, and then let's just make a loop. Well, we're already in a loop. Okay, let's do this. Change my mind. I'm going to put the setup stuff outside the loop, and then we'll use the while loop to just toggle the pins. So we could do it like this. Port D equals, you can do, I'm doing this with binary representation. You could do like 1.7 to set the high bit, but just to make it more visually obvious. 1, 0, 1, 2, 3, 4, 5, 6, those don't matter. Port D equals 0, 1, 1, 2, 3, 4, 5, 6. It's utility delay. Here we go. Frequency 8 million, IO delay. So we should be able to do underscore delay milliseconds. Make something we can see. I think I can see 2 frames a second. 2 frames a second, the frame rate of Star Fox. That should be enough to get something to show up. Because if you recall, under device programming, okay, let's hit set, read. Okay. We already set the fuses for what we want the speed to be, so we shouldn't have to change that manually. I guess we'll know if it's correct. We'll turn it on and see if the lights flip at the right frequency.
Yep, there you go. Looks like the frequencies are all correct. 500 milliseconds per light. Here's a piece of beef jerky, bud. You've eaten more of this than I have so far. But absolutely loves beef jerky. It's his favorite human food. I have this character display from Marlon P. Jones and Associates, which is kind of a cool website to buy stuff from. It's like a wholesaler down in Florida. I want to say I paid $20 for it. I thought it'd be cool to make like a cyber deck or something. So, but yeah, this isn't running off the Arduino. So maybe I could make some sort of like lo-fi cyber deck with this. Cyber Deck 2077. I guess the focus just has to be perfect. So yeah, maybe that could be the first step, is porting the liquid crystal library to the bare metal version of this.
Here's the folder that contains this Atmel project. So I'm going to go in liquid crystal master like this. Usually the nomenclature with this is that actually it'll take the word master off the end of it. So let's grab that out of the zip file, go back over here, and then this is our project file. So this is where everything goes. So I'm going to put that in there. See how that folder, or the liquid crystal folder, is right next to main CCP? CCP? No, not China. CPP. Which one of these is it? Show all files. Yeah, so this will show you everything that's in that folder. So just because you added something to the folder doesn't mean it's necessarily added to the project. So see how liquid crystal has appeared? So I'm going to click on it. I'm going to go to include in project. Now it appears as a solid folder. Well, we don't need all this other crap. I should have just added source. Yeah, screw this other crap. It's just confusing. I'm a changed man. I've abandoned my boy. Now, this is going to have stuff that's not referenced, like all the Arduino stuff. Actually, not too much. The only thing that really makes this Arduino specific is stuff like digital write. So we can just change that to atomic bit changes like we did with port, and that's pretty much all we have to do. Oh, I think it wasn't complaining because I hadn't included it. Include liquid crystal H. So we might have to put a folder prepender in front of that for that to work. Oh, I had to put quotations around it because we're not using the system stuff, which is the brackets. We're pointing to a literal path relative to where we are. Not sure what it's using print for. Well, print must be some... Oh, print is probably like, yeah, because you do like LCD print. But we don't have that because we're not using Arduino, so screw it. Int types, that's sometimes like if you do things like if you want to specify like an unsigned integer of 8-bit size like this, you have to include int types. Well, we definitely can't use print, so we just get rid of that. This works like a lot of these LCDs. Like you send it a command and then you send it data. Yeah, so those are, 8-bit guy, he did a video years back. He like manually drove one of these displays, and he used like toggle switches. It was a really cool video. Hello and welcome back to the 8-bit guy. I'm the 8-bit guy. I have ported Attack of the Petsky Robots to my toaster. There we go. That was obviously essential to the project's success. So here's where the magic really happens. We have the read-write pin, which we can just set to be always right. Then we have the RS select pin, which I think is it's register select. And then the enable pin enables the display. Now this display, since it's 40 by 4 characters, it's 40 by 4 rows, it's actually two HD 44780 interfaces together. So we actually need 2 enable pins, one for the top 2 rows and one for the bottom 2 rows. Yeah, see all these? These are overloaded functions. Because you might say, oh, I want to use an 8-bit interface. Oh, I only want to use a 4-bit interface. I'm not going to use the enable pin. Maybe I will use the enable pin. So like this one here. So see, like for instance, this one, RS, read write, enable, and then the 4-bit interface. It still calls the same initialization sequence, but it's just omitting 4 of the items. One thing I don't like about this particular version of Visual Studio is when you compile it, the errors will kind of it'll show you some errors before others. Like I got rid of some other errors, and now look at all these like true errors, so to speak, that it's shown us. Obviously, these are all things that we can't do because of it's not Arduino. Like pin mode RS output. Now, when you do pin mode or digital write stuff in Arduino, there's a lot of crap that happens behind the scenes. We don't have to do that here because we're going to directly connect it, which will actually save us a lot of time and make the interface faster, which is good because this thing is only 8 megahertz. So in this case, since it said, oh, if you only have this many parameters added to the function call, we're going to go here, in which case we're going to pass a 1 down to here, which is a flag to go to 4-bit mode. But since I want to use 4-bit mode no matter what, we also don't need write either. So basically the number of parameters you pass into this object tells it how you're setting it up. So let's go with the bare minimum, which is 6. What's 40 times 4? It's 160. 160 is not that many. Well, if we only have 1K, because I was going to say we could use the screen as RAM because we have so little of it. Maybe. Well, for now, I'm just going to set it up using write always on. Oh, so see how it's like liquid crystal ... liquid crystal. So whatever code is here will be instantiated or will be run when you instantiate the object, which is what we did right here. And then these, I don't even really need to pass those in because we're going to hardwire it, which I guess we should talk about next. We have to remember any functions we change in the C++ file, we also have to change in the H file. So I'm going to remove these entries that we're not using. This wouldn't break it, but later on, like if we changed what send does, for instance, if we changed it from a 8-bit value to a 16-bit value, if it doesn't match what's in the H file, it'll throw up an error. It'll be like, I've got an error. All right, let's see. So we're going to do a 4-bit mode is going to be a foregone conclusion. Ha 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 ha. Display function. Is display function a variable? It must be. That must be set in the H file. Oh, yep, there we go. See, they're ORing other stuff into it, so they are using it for multiple bits. Well, that's good. Okay. All right, so begin. Columns, lines, dot size. So I don't think we've passed in dot size, so that must be assumed. Since we already know what we want, we can just add this over here. So let's take this, go up here. Well, actually, no, just boom, done. Actually, we don't need any of this. Don't want that. Okay, pin. This is where we're going to start setting the pins. Not should. We need to replace this with our own function. So we have RxTX, which we're probably going to want to keep to do something else with. That's a standard UART. But then we have 6 bits above that. So we have 2 external interrupt requests, 2 timer outputs, and then we have 2 analog, well, not 2 analog comparators, 2 inputs to an analog comparator. Analog comparator is you have 2 voltages that comes in. If one's higher than the other, it sets a 0, else it sets a 1. So you could use it for differential signaling if you wanted, which is actually how USB works. Yeah, so everything would be sent in a nibble, which is 4 bits, 2 nibbles per byte. Yeah, so right now I've got those 2 LEDs on PD6 and PD7, but we could set PD2 and PD3 to be row select and enable. Although we need 2 enable lines. We can stick that someplace else. But I'm thinking we could use PD4, PD5, PD6, and PD7 as the 4-bit access lines and keep them in order. See how it's doing data pin 0? So it's doing digital writes for every single one of these pins, which is really slow. Where we can do it 4 bits at a time because we're going right to the metal. Yeah, see, it just for int 0, I equals less than how many bits, and then if either 8 or 4, that's how far it goes, an increment. So yeah, it's doing like up either 4 or 8 digital writes in a row. Oh, here we go. This is what we want. Write 4 bits. Okay, so we've got the value coming in. So we talked about how we have port D, right? Well, actually, first before we do that, let's gonna take the top 4 bits and make them all outputs. So value's gonna come in as like this. So you're gonna have 4 nulls and then 1, 2, 3, 4. Those are your bits, right? Now in the port, we wanna put it there. Wait a minute. If we do that, that's gonna require 4 barrel shifts, which also takes time. That's going to take 4 clocks. Okay, so if this was a 32-bit processor, we could type value dun equals 4, and it would shift it 4 to the right, and it would do it in 1 cycle. These 8-bit AVRs, it takes 4 cycles. It goes shift, 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 shift. 1, 2, 3, 4 shifts. PC0 might be better because we got 1, 2, 3, 4, but we don't run into the I2C if we want to use it. So that might be a better bet, because then we don't have to do any bit shifting. LSB. So what they're doing here is for each one of the bits in value, they're setting the data pins high or low. Here, I'll draw what it's doing, right? So let's say that's your bit pattern, right? So what it's doing 1 pin at a time is it's outputting the lowest bit. So it does that, and it outputs this 1. Then it does a bit shift to the right, so then the pattern looks like that, and then it outputs that 0. Then it does another bit shift to the right, pattern looks like that, and outputs the 1. One final bit shift to the right, outputs the final 1. So see how this pattern of, if the pattern is 1, 1, 0, 1, it's being serialized. Again, that's also slow, because you're adding digital write functions plus a barrel shifter, or because you're combining digital write functions with a shift. Value should only have a 4-bit value that should ever be put into it, so we don't even really necessarily have to mask off the top bits, I don't think. Yeah, see up here, write bits value. Let's say the value is FF, all 1s, right? So write bits, and it's going to shift it, so it's doing this. Now I'm switching to hex. So let's say FA is the value, right? So it's going to shift FA 4 to the right, which means it's going to send 0F. And then it's going to send this one without anything, which means it's going to send FA, but only the lower portion of it's going to be accessed. So we should mask it. All right. So what's masking? Well, it's really simple. So we take value. Now, see, we have 2 calls going to that. Well, wait a minute. What if instead of doing 2 jumps to this, what if we... Well, no, because it still has 4 shifts going on. We're still doing less shifts, but... Well, okay. One thing at a time. So we'll take value. We'll go and equals F0. So what that's going to do... Oh, I'm sorry. We're going to go and equals 0F. So mask off top 4 bits. So like in the second one here where it sends value, this code down here is only going to be looking at the 4 bottom bits, but the 4 top bits would still be there. Now, the reason we have to worry about that with what we're doing is because we're going to use full port access. So if you go port C equals value, so if that F if this F here was still in place, it would get slapped onto the 4 upper bits, which we don't want. We want them to be unaffected. So to make sure we're unaffected, we actually do this. Port C and equals F0. Now see how this is an inverse? So the value coming in, we have masked off the top 4 bits. And then we're going to take whatever's in port C right now, and we're going to mask off the bottom 4 bits. So let's say port C had this pattern. 11010110, right? We want to keep these top 4 bits because those are the pins we're using for something else. So if we AND that with FF, so this ANDed with F is going to be the same thing, but since this ANDed with 0 is going to be 0, 0. And when I'm talking about ANDing, I'm talking about, bitwise operations. Okay, so you have to AND it with F0, so mask off top bits, mask off bottom 4 bits for incoming data. And then here's the key part. We're not going to equal value. We're going to OR equals. I would hope a lot of you know this. Let's say 11000110. Okay, let's say that's what's in the port C register. Okay, so let's do a bitwise AND with 11110000. And hit equals. And we're left with, so the top 4 bits haven't been changed. The bottom 4 bits have been cleared. Now let's put in 7. So we're going to bitwise OR. So we're going to take what we just typed and we're going to OR it with 7. Now we hit equals. See? So the top 4 bits haven't been changed. We cleared the bottom 4 bits with an AND equals mask, and then we ORed in the 3 new bits that we wanted. Now, again, more advanced processors, it can do atomic bit operations, so you don't have to do it by the port. But this measly little chip, we have to do it this way. Now, this does consume more time than you might think, because when it gets compiled into machine language, it's like, okay, load port C, put into RAM, well, not a register, put into a register, perform the operation, then OR this back in, and then put it back into it. Which means actually actually the compiler would probably do it automatically. Yeah, see this 32 by 8 general purpose registers? So that's 32 bytes of RAM that's in the CPU itself. Even though this is a microcontroller, the RAM of the microcontroller is separate from the CPU, technically. So see how it says data SRAM here? The CPU accessing the data SRAM, I believe, takes 2 clocks, whereas it can access its own registers in 1 clock. The compiler will probably do it for us, but what usually happens with these functions is it will put these as registers, not RAM, which means 1, it doesn't count against your RAM, and then 2, it's faster to access. So in this case, yeah, it would probably load the status of port C into register RAM, do the operation, then take the same value and put the bits into it. Anyway, now that we've done all that, we can get rid of that because it does the same thing. What's pulse enable? Oh, that must be the right pulse. Enable pin low, high, low. Well, wait, if you go low, high, low, if the last thing you did was a low, when you come back into it, it'll already be low. So what's the point of this? I actually have 2 enable strobes that I need to set. Yeah, because this counts as 2 displays. Okay. So let's use PB6 and PB7. So remember when we initialize this, it sets what the enable pin is. Right here. Alright, so that's either, well, it's going to be a number. So let's say we pass it 0 or 1. So 0 will be the first 2 lines and 1 will be the second 2 lines. Oh wait, what if I just pass in a bit map, a bit mask? So let's say 1, 2, 1, 2, 3, 4. Let's enable 0. So port B, okay, get ready. Port B AND equals, and what we're going to do is we're going to have it AND equals the inverse of underscore enable pin, which again is either going to be this or this. So it's going to inverse it, which is going to flip it, and then it's going to do the AND equals, so that'll erase all the pins except for the enable pin itself. Then port B or equals enable pin. Well, actually, if we want to emulate what this does, since it goes high and then it goes low, so yeah, we'd actually want to OR it first. So we OR it, that makes it go high. Then we delay 1 microsecond. There. That should do the same thing. I mean, for instance, here's the enable pin output. So instead of, well, we can just do it back here. Although we should do it in the library, DDR, and that was B, and then we use the top 2 bits. So there. Now they're outputs. So now we can get rid of this, for instance. And we're not using the RW pin, so we can get rid of that. Delay microseconds. Delay 50,000 microseconds. That's a fancy way of saying 50 milliseconds. Actually, I'm going to say milliseconds because it's a lower number. Okay, now we pull both RS and read write low to begin commands. Well, we don't. Again, we're not using the read write pin. We need to pick a pin for row select. We need one more pin. Oh, blah blah. Okay, so we're using those. Blah 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 blah. Chip select. This is pretty useless. Chip select is only used in a microcontroller like this when it's being used as a slave. So that pin doesn't automatically pull other devices low. It's for if another device is trying to talk to this device as a SPI slave, then it would pull SS low and then this device would respond to it. So that seems like a pretty useless pin. So let's go with PB2 for that. Oh, it's on the same port. So PB2 would be 0, 1, 2. So it'd be that one right there. I created an init that takes no parameters. All it does is set display function. Oh, actually, I goofed up. We do need to have one thing in here. We need to have the enable pin because remember, we're actually driving 2 displays. So I'm going to call this object LCD 0, and then I'm going to give it a value of the topmost bit. Oh, actually, I'm sorry. No, it would be the second to topmost bit. Then we're going to create another object, and it's going to have the top bit set. Okay. So basically this one uses PB6 for enable, and this one uses PB7. So now I just need to go through and basically turn everything from Arduino code to, just bare metal code. Like RS pin low, okay, so that's PB2, so we just need the inverse of this. So that's 1, 2, 3, 4, 1, 0, 0, 0. So it's PBB 0, 1, 2, and that's why we set that 1 to be a 0. Same thing with enable pin. Okay, so we start in 8-bit mode, blah, 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 set 4-bit interface. Command, okay, we're sending a function, display. So everything here should be just referencing functions within the object. So as long as we've got rid of all of those like digital writes and outputs, we should be good to go. Now we fix all the errors like this one right here. As I mentioned, needs to be in the H file. So come back over here. Okay, I removed the print object inheritance from Liquid Crystal, which means I'll have to do that stuff manually, I believe using send. Alright, so we'll do the 2 displays and then we'll send the character A to one and the character B to the other.
These are all nicely labeled, so well, at least these 3 are. Put the programmer back over here. So enable 1 is PB6. Enable 2 is PB7. Yeah. That's odd. I need more light in this room. So I believe it's this way. So see, I can hook this up as just one straight 4-bit port. My gosh, this is so dark here. Well, we got A. Where's the other B, though? I wonder if there's something wrong with the enable lines. Let me try switching them around. Oh no, that one's floating now. That's not good. I'm gonna put enable 1 on enable 2. Okay, so the line works. Actually, there's one more thing we can check. So I'm gonna remove the enable 1 line from that, plug the enable 2 line into PB6. So let's see if the character A appears on the bottom 2 rows. Yeah, okay, so it's something with how PB7 is being handled in the code.
I put in some delays up here between starting each display and then starting the next display. I think that should help. If we go, so let me restart it, and you should see that. Yeah. So this is a counter, and that's drawing characters. So they start at the same time. Now, if I go in and remove these generous delays, I think that's when we start to have problems. All right. So it's just going to go full speed, and it still worked. So. All right, because yeah, we don't have the fancy Arduino print function. All we can do is write data to the screen. So if you want to write an A, you have to write a 65. And if you want to do like print hello world, well, you can't because you don't have a print function. I guess we could make one. Well, that's weird. I'm going to just do a power cycle and restart. Yeah, that was a little fluffer nutter there. Huh, well, maybe we don't need those extra delays. Yeah, I think I might leave him in there just to be safe, though. Yeah, so see how this is virtual? I think the reason it's doing that, yeah, and they had inherited from print, so they must have, yeah, the Arduino function must be able to use this virtual size t write to print to it. So I guess that's the only thing that it would connect to is the write command. So what if we wanted our own? Oh, right, the H file defined it. Never mind. Okay, so. Okay. While there's anything at the, well, while that's not 0, basically. That's so, what is it, right? Write the string and then increment the pointer. I think that should work. We don't have an H file for our file, so I have to put any functions above main, otherwise they won't work.
Oh, good, it worked. See, but I probably have to make, if I'm going to use this as a screen, I'm going to have to make a handler that says, okay, like what if the cursor was over here and you printed hello world, and then, oh, well, you have to jump to the next display. So you'd really need, yeah, you need to keep track of where the cursor is. Yeah, I guess that makes sense. Because, yeah, you can set the cursor. You can say, oh, LCD, go to cursor 00 or 39.1 or whatever. But you'd also have to know on your own side where it was. Because, like, if you wrote past this, well, here, I'll just show you. Like, if we put the cursor, I'm going to do LCD 0, set cursor 38.1. So it'll start here, and then it'll wrap around up there, I'm guessing. Actually, I'm not guessing. That's exactly what will happen. Oh, look, it's exactly what happened.
Set cursor int, now let's use a char. X, char y. We use a char to ensure that it's a byte. Remember, we only have 1K of RAM. All right, so if it's less than 2, then we're talking to screen 1. So that's LCD 0, set cursor. X is going to be the same no matter what. And then Y would also be the same. Okay, that should give us, that should put the cursor wherever we need it to be. But we also want to keep a local copy of it. So I'm going to do xpos, char xpos equals 0, char ypos equals 0. Well, actually, we could build that into print. Like we could have, we could have char x, char y, char the string. Well, wait a minute. We also want x. Okay, yeah, so actually x position. If x position is more than 39, so did we roll over horizontally? So no matter what, x position is going to revert to 0, but what happens to the y position? So y position, okay, well actually, yeah, we need to look for if we're going to change screens, which means this would also change. X position, y position, and then let's do active display equals 0. Okay, there's probably a better way to do this, but oh, that seems awfully sloppy because we're going to have to do a if statement on every character. Okay, just for now, well, make it work, then make it efficient. If x position is more than 39, x position equals 0. Okay, so then we're going to look for a rollover. If y position, so this is after it's, well, carriage returned or whatever. So if y position equals 1, that means we're going to go to y position 2. Well, that's obvious. But then also we're going to switch to display. So active display now equals 1. Yeah, I think we can put the objects into an array. All right, we're not using dot size, so let's change that. Let's put the enable over there. So let's grab this. Grab the enable, bring it there. Put it here. Put the enable equals enable here. Create 2 of those. Okay, so it'll be LCD 0 begin. And then what was it? 4? Yeah, okay. And then LCD 1 begin. All right, so set cursor X, Y, blah, blah, blah. All right, so now we can, if we have active display, we can automatically just, well, we can do this. LCD active display set cursor, just like that. So if Y is more than 1, then subtract 2. Okay, now we can replace this tomfoolery with this. Right, well, let's copy it. Remember, got to be lazy. Got to go fast. Programming is a laziness contest. And whoever wins, we lose. All right, so write a character to the active display. If X position is more than 39, reset X position. If Y position, so no matter what, let's just do that no matter what. So if Y position equals 2, did we roll over? Roll to next display. Active display equals 1. And then, of course, if we roll past the bottom, if Y pos equals 4. Oh, wait, I forgot. I made a robot fish. Alexa, turn on the robot fish. Can you hear it? Go get it. Yeah, go get it. Haha, that got rid of him. Okay, where was I? Okay, and then active display equals 0. Okay, let's start at 35 over 1 line down and print. I'm sorry, Dave. I can't let you do that.
Okay, there we go. It worked. I'm sorry, Dave. I can't let you do that. All right. So that was starting at 35 over 2 down. So if I type more crap, it should roll into the top hand side. This mission is too important for me to let you do stuff. I know that's not the quote. I don't care. Cool. It worked. Do you want me to pick you up or something? You have been knocking spice things off the shelf lately, and that's bad. That is not what cats are supposed to do. Well, actually it is, but...
Data memory usage, 135 bytes. Oh my gosh. That's like 13%. So I think we could just do this with just one object, because once you set it up, the only thing you change is the enable pin. Void. Set enable. Which. Actually, if we called that before begin, yeah, that should work. Because we can just make one object, then we'll just change that variable inside of it. Yeah, although I guess we could call it with begin as well. The important thing is we need to call it before like the right functions. Again, well, let's just do this simply and then we'll do it hardly. Okay, let's go back to only having one LCD object. And let's do this. So this part, we can do that the same. Because we still have to start up both chips. So start them both up. Now in this case, now when we're calling clear, we will have to indicate which one we're clearing. So LCD set enable. Oh man, I'm hungry all of a sudden. What did I eat for lunch? I can't remember. we could, instead of sending active display, we could send the enable pin, basically. Yeah, choose display if active display equals 0. Although I believe this is 40. Yeah. So basically, active. Okay, so this, we don't need this. And we don't need this. So really, you just call choose display whenever you change active display. I guess it doesn't matter if you, yeah, I guess you can just call it once. That technically would save a little bit of flash memory. Well, I need to clean it up some, but it still works. And we saved some memory because it's 2 objects, but there's, yeah, the code is static, but the data in each object would be different. So that's why we saw, oh look, we got rid of 1 object and we saved 1 object's worth of bytes. But hey, when you only have 1K, every byte counts. Actually, I think we can get rid of active display. We could just have choose display. We could just pass it a value 0, 1. Okay, so active display 1. Because really, you only have to change it every so often. Yeah, because you're setting the RAM, or you're setting the variable over here. It's either this display or that display. So once you change it, every time you do a write command, you don't have to change it again because you already changed it once. Because that RAM is held over there in that object.
Well, there you have it. We got one of the last mass quantity available microcontrollers available from DigiKey, the ATmega 8. Then we made our own custom OshPark breakout board for it. And then finally, we converted the Arduino LCD library to work bare metal on that microcontroller. All right, so I think this has been a long enough video. What I want to do is try to make this in some sort of cyber deck. We got to see what we can do with that chip. So I guess there's going to be more than one part of this video. So we'll see you in a future installment of the Final Microcontroller. Video is still going. Not done yet.
Ugh. Milk bread, get me out of here.
And he thought he could get me because I didn't know the meaning of the word kestrel.